Welcome you in the lecture series of random processes, detection and estimation. It is 11th lecture of this series. In the previous lecture, we have discussed Neyman-Pearson detection in parametric detection class in simple hypothesis testing. In this lecture, we will discuss more about the detection theory. The outline of this lecture are: we will discuss about simple hypothesis testing, where we will discuss about Neyman-Pearson in non-Gaussian noise and the receiver operating characteristic ROC and base risk and Bayesian detector, and then we will discuss minimum probability of error. And in the objective of this lecture, you will able to explain how the receiver operating characteristic ROC describe the performance of Bayesian or Neyman-Pearson criteria, and what is the bias risk and explain minimum probability of error. Now we will discuss Neyman-Pearson testing in non-Gaussian noise. Consider two hypotheses: H naught, that is belongs to xn is equal to omega n, means in the hypothesis H naught there is only noise, and hypothesis H1 corresponds to xn is equal to a plus omega n, where n 0, 1 to n minus 1. So this is the example of DC level in a non-Gaussian noise, and the PDF of the noise p omega n, it will be the pi n 0 to n minus 1, and the PDF of xn under hypothesis H naught, and under hypothesis H1 the PDF it will be pi n 0 to n minus 1, and the PDF of xn minus a. So now the NP detector decide H1 or H naught if the PDF under H1 divided by PDF under H naught is greater than less than a threshold value gamma. This means when this ratio is greater than threshold value gamma, then we will decide H1, and when this ratio is less than gamma, then we will decide H naught. If the PDF of the noise is a Gaussian mixture, then we can have the PDF of the noise will be 1 by 2, 1 by under root 2 pi e to the power minus 1 by 2 omega square n plus 1 by 2, 1 by under root 4 pi e to the power minus 1 by 4 omega square n. So the detector will be pi n 0 to n minus 1, 1 upon 2 under root 2 pi e to the power minus 1 by 2 xn minus a whole square plus 1 by 2 into 1 upon under root 4 pi e to the power minus 1 by 4 xn minus a whole square divided by n pi n 0 to n minus 1, 1 by 2, 1 by under root 2 pi e to the power minus 1 by 2 x square n plus 1 by 2, 1 by under root 4 pi e to the power minus 1 by 4 x square n, and it will be greater than less than some threshold value gamma. There can be no further simplification is possible due to lack of sufficient statistic of A. We will explain non-Gaussian detection in coming lectures. Now we will discuss the receiver operating characteristic ROC. An alternative way that define the detection performance of NP detector is the plot between PD and PF, means plot between probability of detection and the probability of false alarm. This type of way is known as the receiver operating characteristic. Now, you know the probability of false alarm will be Q gamma dash upon sigma square by n, and it is 4 when xn is equal to a plus omega n. and probability of detection q gamma dash minus 1 upon under root sigma square by n, or probability of detection. You can write this as you can see in the previous lectures, q uh, q minus q inverse pf minus d square deflection coefficient, where d square deflection coefficient is na square upon sigma square. So the plot between PD and PF, you can see the plot with the different value of deflection coefficient, and the ROC curve should always be above 45-degree line, because for d square is equal to 0, it will be the 45-degree line, and the family of ROC generates for different values of deflection coefficient. Means for deflection coefficient is equal to 1, the curve will be like this, and for deflection coefficient d square is equal to 2, the curve will be like this, and d square very greater than 1, it will be like this. So as you can see, d square increases, the value of probability of detection obtained for a small value of probability of false alarm also increases. And when d tends to infinity, here you can see the ideal ROC is obtained, means probability of detection is 1 in this case for any value of probability of false alarm at d tends to infinity. Further, as the threshold value gamma varies, this threshold value gamma varies from minus infinity to plus infinity, the point PF and PD along the ROC. So if the threshold gamma tends to minus infinity, then the detector always decide H1, and the PF and PD are 1 at this point. So at this point PF and PD are 1, and detector always decide H1, hypothesis H1. And if threshold tends to plus infinity, here in this direction the gamma is increasing. So when this is tends to plus infinity, then the detector never decide H1, and PD and PF are here will be 0 0, and this value is gamma dash, and the slope of ROC curve at any point TFPD equal to the threshold value gamma dash. Also the points of ROC curve should satisfy the probability of detection always greater than equal to probability of false alarm. This is the curve of ROC, and you can see this is the concave curve. Let us consider one example. Let a random variable y is equal to n plus lambda theta, where theta is either 0 or 1, and lambda is a fixed value, fixed number between 0 to 2, and n is having the uniform distribution between -1 to 1, and we have given two hypotheses. H0 belongs to when theta is equal to 0, and H1 corresponds to when theta is equal to 1. We have to decide between the two hypotheses. So find the NP decision rule to decide H1 for when for PF lies between 0 to 1. So you know, when the hypothesis H0, the output Y will have the uniform distribution -1 to 1, and because in this case theta is 0, and when the hypothesis H1, the output Y having the uniform distribution from lambda -1 to lambda +1. So we can sketch this from -1 to 1. It is under hypothesis H0, and from lambda -1 to lambda +1 it is under hypothesis H1. So if I consider the threshold here, and so the region R1 will be this is the critical region, and region R0 will be this, and the The probability of false alarm will be given by this shaded region, and the probability of missed target is given by this shaded region. So if gamma is the threshold, the probability of false alarm will be, because gamma is the value of gamma threshold is here from gamma to 1. This is the probability of false alarm, the reason of probability of false alarm. So we integrate from gamma to 1 by 2 dy, and it will be 1 by 2 1 minus gamma, and here this 1 by 2 is because there is uniform distribution from -1 to 1, and when there is uniform distribution, and the PDF of this uniform distribution will be 1 upon 1 minus 1 minus, which is 1 by 2. So that's why I have written this PDF of this uniform distribution when it is between -1 to 1. So the value of gamma is from here is 1 minus 2 PF, and so the NP detector decide H1 or H0 if Y greater than less than gamma, or you can write here Y greater than less than 1 minus 2 PF. This means when the value Y greater than 1 minus 2 PF, we will decide H1, and when the value Y less than 1 minus 2 PF, then we will decide H0. And the probability of detection is PD from gamma to gamma lambda plus 1, because the region R1 is from gamma to lambda plus 1 by 2 dy. So it will be 1 by 2 lambda plus 1 minus gamma, or you can write it as PF plus lambda by 2. So the ROC, sketch the ROC here. So, the PF is 1 upon 2, 1 minus gamma, and PD is PF plus lambda by 2, and gamma is 1 minus 2 PF. So sketch between PF and PD, you can see here when lambda is equal to 0, this will be the 45-degree line, and when lambda is equal to 1, PF PD are 0.5, and here when gamma tends to -1, the receiver always decide H1, and PF and PD are equal to 1 here, and when gamma tends to 1, here the receiver never decide H1, and the value of PF and PD are 0 at this point, and when lambda tends to 2, the probability of detection will be 1 at this point for any value of probability of false alarm. Now we will discuss Bayes risk and Bayesian detector. In previous detection problems, we have assigned probability to various hypotheses. In Bayesian hypothesis testing, not only prior probabilities are assigned to each hypothesis, but also the cost Cij is assigned to each of the errors. Cij means the cost if we decide Hi, but Hj is true. So C10 means we decide that the part of a machine is satisfactory, but it is proves that to be defective. The entire product may be defective, so we have a large cost of C10. And C01 means we decide that the part of a machine is defective where it is not. We have a small cost of the part C01. In some applications, all type of errors are not equal importance, so different costs will be assigned to different error to optimize the detection performance. The objective of detection is to minimize the expected cost or Bayes risk that will be defined by summation I0 to 1, summation J0 to 1, Cij P Hi by Hj means conditional probability when you have decided Hi but Hj was 2, and the probability of Hj, this probability Phj is the prior probability of jth hypothesis, and this is the conditional probability of detecting Hi when Hj is true. So I can write the bias risk as R is equal to C00 P H naught by H naught P H naught plus C10 probability H1 by given when given H naught and probability of H naught plus C01 probability H naught when H1 is true and probability of H1 plus C11 probability of H1 when H1 is true and probability of H1. So I can also write it as C00 because this is the joint probability. Combinedly it is known as the joint probability from the Bayes rule. So I can write it as C00 probability combinedly H0 and H0, C10 probability H1 C01 probability joint probability of H0 H1, C11 joint probability of H1. So here if C00 is equal to C11 is 0, means there is no cost assigned to the correct decision, and if C10 is equal to C01 is equal to 1, means we have given the same cost to the error, then the bias risk will be probability H1 given H0 and probability of H0 plus probability H0 given H1 and probability of H1. And in this case, when C00 C11 is equal to 0 and C10 C01 is equal to 1, this bias risk is known as the probability of error. And if C10 greater than C00 and C01 greater than C11, that is the cost of error is higher than the cost of correct decision. The test that minimizes the average cost or bias risk is known as the bias test. The detector that minimizes the bias risk is to decide H1 or H0 if likelihood ratio test means the PDF under hypothesis H1 divided by PDF under hypothesis H0 greater than less than C10 minus C00 divided by C01 minus C11. And I also can write this the joint PDF from the Bayes rule. The probability X given H1, probability of H1 divided by probability X given H0 and probability of H0 greater than less than C10 minus C00 divided by C01 minus C11. So from here I can write the probability X given H1 divided by probability X given H0 greater than less than C10 minus C00 divided by C01 minus C11 into probability of H0 divided by probability of H1. These are the prior probability, and this is the threshold value gamma. So, and this is the conditional likelihood ratio, where the PDF is given in the condition form, and here the threshold gamma is also depend on the prior probabilities of each hypothesis and also the cost related to each error and correct decision. This is known as the Bayesian detector. Let us look at the proof. If C00 is equal to C11 is equal to 0, C10 is equal to C01 is equal to 1, then the bias risk will be the probability of error, at this condition, and the bias risk, is J0 to 1 and I0 to 1, Cij probability Hi given Hj and probability of Hj. So you can write here the bias risk is C00 probability H naught by H naught, the probability of H naught plus C01, conditional probability of H naught when H1 is given, into probability of H1, and plus C10, conditional probability H1 when H naught is given P H naught, and C11, the probability H1 when H1 is 2, and the probability of H1. So I can write it as C000 and probability of H naught, and this probability of H naught when H naught is 2, this means you have to integrate in the region of R naught, because you have decided H naught, and the PDF of Tx by H naught means this means the PDF under hypothesis H naught. So it will be C00 probability of H naught integration R naught P x by H naught dx plus C01 probability of H1 and P H naught by H1. It will be the integration R naught, because you have decided H naught but H1 is 2, and you have to integrate under the hypothesis PDF of under the hypothesis H1 means P x by H1 dx plus C10 probability of H naught integration R1, because you have decided here H1 but H naught is 2, so the integration of the PDF under hypothesis H naught, and C11 PH1, here you have decided H1, so the integration will be in the range of critical region R1, and the PDF under hypothesis H1 Px by H1 dx. So from here you can see that region R1 is the observed sample when where we decide H1 from the observed sample, and R0 the observed sample from which we have decided H0, and also the integration R0 P x by Hi dx, it will be 1 minus integration R1 P x by Hi dx. So from this probability property, the bias risk can be written as C01 PH1 plus C00 PH0 plus integration R1 C10 PH0 minus C00 PH0 into P conditional probability P x by H0 plus C11 PH1 minus C01 PH1 and conditional probability P x by H1 dx. And if we decide H1, this means C10 minus C00 PH0 and P conditional probability Px by H0 will be less than C01 minus C11 PH1 and conditional probability Px by H1. Since C10 greater than C00 and C01 greater than C11, we get the conditional likelihood ratio will be greater than less than C10 minus C00 and C divided by C01 minus C11 probability of H0 divided by probability of H1, and this is the threshold value gamma. So it is the proof of this. Now we will discuss minimum probability of error. As I told you, in some cases we don't assign a cost if not error is made in the decision. This means C00 C11 is equal to 0, and also we assign equal cost to the errors, means C01 is equal to C10, it is equal to 1. Now the bias risk become the probability of error, you know this thing. So the probability of error can be given as it is equal to bias risk R, and it is probability, conditional probability H0 by H1 probability of H1 plus conditional probability Ph1 by H0 and probability of H0. So if the Bayesian detector is used, we can minimize the probability of error, and we decide H1 or H0 if the conditional likelihood ratio greater than less than probability of H naught by probability of H naught means the prior probabilities of the hypothesis, and it is equal to the threshold value gamma, because here C10 and C01 are 1 and C00 and C11 are 0. So here the threshold value only depend on the prior probabilities of the hypothesis, and this is similar to the NP test. We compare the likelihood ratio to the threshold value, which determines the prior probabilities of each hypothesis. Consider the on-off king communication problem, where we transmit either S0 is equal to 0 or S1n is equal to A at the receiver. The two hypotheses are, under hypothesis H0, we have xn is equal to omega n, where n0 1 to n minus 1, and under hypothesis H1 the observed data is xn is equal to a plus omega n, means DC level in Gaussian noise, where a greater than 0 and Wn is the white Gaussian noise with variance sigma square. And also let the probability of H0 and probability of H1 are equal, means 1 by 2, so they are equally likely, both the hypotheses are equally likely. To find the probability of error in this case, you know, the receiver that minimized probability of error decide H1 or H0 under the Bayesian test, means the conditional likelihood ratio will be greater than less than equal to prior probability H0 divided by the prior probability of hypothesis H1. This means this is the threshold value which is depend on the prior probabilities. So if the this conditional likelihood ratio greater than this threshold value, we will decide H1, and if this conditional likelihood ratio less than the threshold value gamma, then we will decide H0. Now and here, because these two are equally likely, so the value is 1 by 2, 1 by 2, so the threshold value here is 1. Now the PDF under hypothesis H0 H1, it will be 1 by 2 pi e 2 pi is to the power n by 2 into 1 by sigma is to the power n is to the power minus 1 by 2 sigma square summation n0 to n minus 1 xn minus a whole square divided by the PDF under hypothesis H0, means 1 upon 2 pi is to the power n by 2 minus 1 by sigma is to the power n is to the power minus 1 by 2 sigma square summation n0 to n minus 1 sigma square n, greater than less than threshold value gamma. And taking natural log, you will get 1 by 2 sigma square minus 2a summation n0 to n minus 1 xn plus na square, greater than less than 0. So from here you can have 2a summation n0 to n minus 1 xn greater than less than na square, or you can write it as 1 by n summation n0 to n minus 1 xn greater than less than a by 2, or I can write it as, because it is the sample mean, x bar will be greater than less than a by 2. So when the sample mean greater than a by 2, we will decide H1, and the sample mean less than a by 2, we will decide H0. A here, A is the DC level which we are transmitting. So this is the same as for NP criteria, except for the threshold. So here the mean value of this sample mean under hypothesis H0, it will be the mean value or expected value 1 upon n, n is to the summation n0 to n minus 1 omega n, because under hypothesis H0 the received is the noise only, so it is the 1 by n summation n0 to n minus 1 expected value of noise. And you know, the noise is white Gaussian noise with mean 0 and variance sigma square, so the mean is 0 here. And similarly, the expected value of a sample mean under hypothesis H1, it will be 0, and variance of a sample mean under hypothesis H0, it will be the variance 1 by n, summation n0 to n minus 1 omega n. This means 1 by n square summation n0 to n minus 1 variance of sigma square and omega square, and you know the variance of noise is omega sigma square, so it will be 1 by n sigma square. This means sigma square by n. And similarly, variance under hypothesis H1, it will be sigma square by n. So here you can see under hypothesis H0, the sample mean will have the PDF, Gaussian PDF with mean 0 and variance sigma square by n. And under hypothesis H1, the sample mean have the Gaussian PDF with mean A and variance sigma square by n. So here the variance are same, but mean are 0 and A. And if the sample mean is greater than A by 2, then we will decide the hypothesis H1 is true, and if the sample mean less than A by 2, then we will decide the hypothesis H0. So here, now the probability of error is 1 by 2 P H0 by H1 plus P H1 by H0. This means 1 by 2 probability P H0 when H1 is given means probability of a sample mean less than A by 2, because you have decided the H0 given H1, plus probability of you have decided H1 means the sample mean is greater than A by 2 given the hypothesis H0. So in the first part we will calculate the probability when the sample mean is less than A by 2 when hypothesis H1 is true. It will be the 1 minus probability sample mean greater than A by 2 when H1 is true. So you can write it as 1 minus a sample mean greater than A by 2 means from A by 2 to infinity you have to integrate from A by 2 to infinity, and the PDF under hypothesis H1 means 1 upon under root 2 pi e to the power minus x minus a whole square upon 2 sigma square by n. As the mean of the sample, the variance of the sample mean. So from here you can have 1 minus a integration from A by 2 minus a upon sigma square under root sigma square by n to infinity 1 by under root 2 pi e to the power minus x square by 2 dx, and from the definition of the cumulative distribution function, it will be 1 minus q a by 2 minus a upon under root sigma square by n. So it is in the form of q function. And in the second part, the probability when sample mean greater than A by 2 when H1 is true, it will be the integration from A by 2 to infinity 1 upon under root 2 pi e to the power minus x square by 2 sigma square by n dx. So it will be the q function q A by 2 divided by under root sigma square by n. So now we have measured this. So put this value from part first and second in equation first. You will get the probability of error 1 by 2 1 minus q a by 2 minus a divided by sigma square by n plus q function a by 2 divided by under root sigma square by n. So we can write it as 1 by 2 q a by 2 divided by sigma square by n plus q a by 2 divided by under root sigma square by n. So from here you can have, because 1 minus qx is equal to q minus x, so from this you may have this quantity. So it will be equal to 1 by 2 into 2q Na square upon 4 sigma square, under root Na square upon 4 sigma square. So here the probability of error will be Q under root Na square upon 4 sigma square. So the probability of error in the form of complementary error function, it will be 1 by 2 ERFC Na under root Na square upon 2 into 4 sigma square. So the probability of error decrease monotonically with Na square by 4 sigma square increasing, which is the deflection coefficient of this problem. So here this is the deflection coefficient Na square upon 4 sigma square. Now consider another example. Consider the binary communication problem where we transmit either S0 0 is equal to 0 and S1 0 is equal to 1. There are two hypotheses at the receiver. Under hypothesis H0, X0 is equal to omega naught, and under hypothesis H1, X0 is equal to 1 plus omega naught. And where omega naught is the white Gaussian noise with mean 0 and variance 1. At the receiver, we observe that X0 is equal to 0.6, and suppose that probability of false alarm is 0.25. So the first part is using NP test, determine which signal was transmitted, and the second part is find the probability of miss, means probability of PM or second type of probability of error. So from the NP test we decide H1 or H0 if the likelihood ratio means the ratio of PDF under hypothesis H1 and the PDF under hypothesis H0 is greater than or less than threshold value gamma, and you can write it as 1 upon under root 2 pi e to the power minus x naught minus 1 whole square upon 2, and 1 by under root 2 pi e to the power minus x square naught, because here taking natural log you will get x naught minus 1 by 2 greater than less than log e, or you can write at x naught greater than less than 1 by 2 log e gamma, and this is new threshold value 1 by 2 plus log e gamma. This is the new threshold value gamma dash. And so from this you can have the critical region R1 will be the sample space when the sample space greater than gamma dash. The probability of false alarm is 0.25, and the probability of false alarm means probability of deciding H1 when H0 is 2, means probability when the observed sample greater than gamma dash when H0 is 2. So it will be gamma dash to infinity 1 by under root 2 pi e to the power minus x square ds, means this is the PDF under hypothesis H0. So after integration you will get 1 minus cumulative distribution function 1 minus phi gamma dash, and this is equal to 0.25, and so gamma phi dash will be 0.75, and from the table you can find out for which value this cumulative distribution function having the value 0.75, and it is the value 0.674. So gamma dash here is 0.674. So the NP test to decide H1 or H0 if the observed sample greater than less than 0.674, means if the sample mean having the value greater than 0.674 we will decide H1, and if the sample mean having the value less than 0.674 we will decide H0. But in the question you have given X0 is 0.6 and it is less than 0.674. So the NP test decide that S0 0 is equal to 0, means 0 was transmitted. In this case no signal was transmitted, only noise present at the receiver. The NP detector decides this thing. And the second part was to find the second type of error, means probability of miss. And you know probability of miss means the probability of H0 when H1 is true, means the probability of a sample mean less than gamma dash when H1 is true. And it will be 1 upon under root 2 pi integration minus infinity to gamma dash e to the power minus x0 minus 1 whole square by 2 dx. And this will be equal to 1 by under root 2 pi minus infinity to 0.674 e to the power minus x0 minus 1 whole square by 2 dx. And this will be equal to 1 by under root 2 pi minus infinity to minus 0.326 e to the power minus y square by 2 dx. So from here it will be from the definition of cumulative distribution function, it will be phi minus 0.326, and from the cumulative property it is 1 minus phi 0.326, and from the table you can find out the value of this phi 0.326. It will be 0.628, and the value of the miss target, it will be the 0.372. so it is the second type of error, and it is 0.372. So far in this lecture we have discussed about receiver operating characteristic ROC, bias risk, and Bayesian detector. And this was the 11th lecture of the lecture series of random processes detection and estimation. In the next lecture we will discuss about maximum likelihood detector, maximum a posteriori detector, map detector, and minimax detector. Till then, thanks for listening this lecture. Thank you.